We're going to start with one formula. Okay, and this is Mrs. Pyre being lazy and not writing in her vector arrows. But because we have acceleration in the formula, this is displacement and velocity. Okay, so if we were looking at what do we have in this equation? We don't have VI. We would use this equation if we were provided VF, A, D, or T. You would need 3 of the 4 to be the reason why you use this equation. Okay? If we looked at the flip side of that one, if we looked at the flip side of that equation, we have VI, we don't have VF. So if we were looking for final velocity, this would not be an equation that we use. We have A, we have, can I do what? Speak about it? Do you want me to go over it in dark pen? Okay, that's why I did one in each. Okay, is that better, Avery? Okay. Another formula that we use, D is equal to VF minus VI divided by 2, plus, I was going to say it's the average, multiplied by time. It's the average of the velocity multiplied by time. So we have VI, we have VF, we don't have A, we have distance, and we have time. So you would always need a minimum of 3 out of 4 of those to use those equations. So if the problem never mentions the word acceleration, don't try and use D equals to VFT minus 1/2 AT squared, or D is equal to VIT plus 1/2 AT squared, or A is equal to delta V over T, or A is equal to VF minus VI divided by 2 times time. Don't use those ones. A isn't in the question. They won't give you what you need. Now, having said all that, A is equal to VF minus VI divided by time, which is also equal to delta V over T. So in our notes, we broke them out as 2 separate formulas and said, memorize this one. That's what our notes say. But our data sheet actually has A is equal to delta V over T. So do you need to memorize this one when the data sheet tells you A is equal to delta V over T? Because by this point, the change in is something minus something. Okay? So I have VI, I have VF, I have A, I don't have distance, and I have time. So again, you would need 3 out of 4 of those to be able to solve a problem. And then this one is the one that Avery mentioned. VF squared is equal to VI squared plus 2AD. So which piece of information do we not have in this formula? T. We don't have T. We have displacement, acceleration, final velocity, and initial velocity. And you would need 3 out of the 4 pieces of that information to solve it. And when we're talking about, this is the big key piece here. Okay, when we're talking uniform accelerated motion, never use velocity is equal to displacement over time. And then I say that, and then I'm going to teach you something different, and you're going to go, what, that doesn't make sense, you said, but it won't be uniform. Okay, this is just a quick summary chart. That's why we always list our information down the left-hand side of what we know, so that when we go back and we are looking at our data sheet, it helps us figure out which formula are we actually wanting to use to solve the problem. And right now, kinematics is like Mrs. Johnson's straight ahead. They're just one-step formulas. But eventually, as we move into dynamics and circular motion and sound and all those pieces, we might only have 2 out of 4 pieces of information. And so then we have to do another calculation to get that third one so that we can solve the initial problem. And then when we get into physics 30, they're always 2-step problems and sometimes 3 steps. Okay? Which I know you'll all be excited to come back for. All right, let's look at graphs. Oh, yeah, you can see. Okay. Uniform accelerated motion graphs. We're going to be looking at distance versus time, velocity versus time, and acceleration versus time. And if we're talking acceleration, we're going to make one correction. We're going to call this what? We're going to call that displacement. That is the more accurate term to use. We have acceleration and deceleration. This is a positive and this is a negative. If I saw a graph like this, you should by now, I think everybody in here has done math or is in math 30 at some level. Okay, you should have seen curved graphs. This is what we call an exponential graph. Something is changing faster than something else. In this one here, distance is increasing rapidly as time is carried along in a straight time. Okay? What do you think is happening? Let's look at this. Time is increasing and my distance happens rapidly and then it levels off. In terms of acceleration, what do we think is happening? Our distance isn't increasing as rapidly towards the end. What could we say about acceleration? What could we say about a vehicle? It's slowing down. Okay? If I looked at this kind of graph, what could I say about that? Yeah, I don't have a huge increase in distance until this time, and then it rapidly increases the distance. So this line is speeding up. Okay, so just from a graph, we've been able to tell if something is slowing down or speeding up. Now, if I was looking at a velocity versus time, what would uniform acceleration be? What kind of graph do you predict? Kind of graph do you predict in a velocity time graph if we're talking in terms of uniform acceleration? Do we expect it to be horizontal? Do we expect it to be curved? Or can we expect there to be a slope? A what? Say it out loud, Kyle, with confidence. A slope. Okay? I don't start it at 0 because we're in motion and we're accelerating. So this is us leaving Fairview at 60 kilometers an hour, and we are steadily increasing from 80 and then up to 100. Once we hit that 100 and lock it in at cruise control, what do you think the graph would do at that point? It would level off. Exactly. It wouldn't come back down. It would then go flat because then that velocity is being maintained. Okay? So there's some information that we can get from this graph. What do you think the slope will tell us? How do we find slope again? Rise over run. The change in y over the change in x. And what is y? Velocity. So the change in velocity over what's x? Time. What does delta V over T look like? Say what, Krista? Yeah, that's how you solve it. But we just learned in our last, like the page before, delta V over T is what? Acceleration. So the slope of a velocity time graph will tell us acceleration. Okay, Kyle? Sure. Now, we learned something else about graphs. We learned about area. How do we solve area? Length times width, or if I was to do this, you would see two shapes show up. Base times height divided by 2. So if I looked at length times width, I would have velocity times time. What does velocity times time give us? Displacement. Excellent. So the area under a velocity time graph will give us displacement. And it's the total area. It would be this area plus that area, A plus B, the total area underneath. Okay, last graph. This is the only downfall to using a Sharpie as it bleeds through the paper. That's okay. Acceleration versus time graph. If I am constantly accelerating, what kind of line will I have on my graph? Straight up, which means like this, you're saying? Like a slope? Like that? Would that be uniform if my acceleration was constantly going up? Say that last one with confidence. It will just be straight. You are uniformly accelerating at the same rate. That's what remember uniform velocity? Avery said it, and somebody else over here said it, I think Rayleigh maybe, that if we hit that 100 kilometers an hour, our velocity would level off. Well, if I'm at a constant acceleration, if I'm accelerating at the same rate, uniform acceleration, then I would have a flat line. Down here on this line, I would not be accelerating because that would be 0. But up here, I'm accelerating at a constant rate. So can I do a slope formula with this line? No. But what can I do? I could do area, and area is length times width. And so I would have acceleration times time. And what does acceleration times time look like? Let's look. Up here, we said A is equal to delta V over T. If I did A times T, what would that be equal to? Be velocity. I could figure out what the velocity is at 10 seconds, at 20 seconds, at 2 hours, at 5 hours. Okay? The change in velocity. I should be more specific. Now this one here, you can do a mathematical calculation, but we're so far from that level of math, we don't worry about it. And it would tell us acceleration. Okay? Clear as mud? You want to see the bottom? Absolutely. So this graph gives us all kinds of information, and so you might not see it. It does this and this. Oops. Does this big swoop. That's what it's doing. Okay? This says A, B, C, D, E, F, and G and H. Okay. Let's describe the type of motion and the direction of each section in the following graph. So, B and E. Who would like to hazard a guess what's happening at B and E? This is the E right here. What can we say? This is a displacement time graph. This is the base graph. What can we say at B and E? Aiden. So what would that mean? If we're not covering any distance, we must be, and the fancy word for that is at rest. Good job, Aiden. The object is at rest. What about at A and C? Those are both linear slopes. Oh, love that. What's another way to say uniform motion? Constant velocity. Okay, now the thing said type of motion and the direction. What can we say about the direction? Okay. What could we contrast between A and C? The what? The slopes. What about the slopes? The different angles. What's that going to tell us, Avery? Acceleration. So what could we say? We could say that C is moving faster than A. Okay, it has a faster speed or a faster velocity. Good, good, good. You guys are making this easy. Okay, here's D. What do we know about D? In relation to A and C, what do we know about D? Okay, so let's start off with it's still constant velocity. And if we were to say a negative direction, Daniel, what's another way, a layman's way of saying it? Okay, it's in the opposite direction. Okay, good. What can we say about this piece here of F? Which means what? It's a graph we just drew. Speeding up, which we call, there you go. It's speeding up. Which is acceleration. In which direction? Do we know? Can we tell? In the positive direction. Oops. Good. Okay, let's look at G. This is going to be kind of weird. Look closely at it. What's happening? Why do you say that, Daniel? But why did you use the word acceleration instead of deceleration? Kate, you can't use slowing down and acceleration in the same sentence. They're opposites. So you're right, it is acceleration. It's in the opposite direction. What we see here is that we still have, even though we're going in the opposite direction, if we were to cut this and flip it, it's still accelerating. Okay? So you were right. Just a little bit of a struggle on your reasoning. That's okay. We're learning. H. What can we say about H then? It would be one of your favorite letters, yeah. What can we say about H? So if this is acceleration, where we have an increase of distance over time, here we see a what? A decrease of distance over time. So if I'm decreasing my distance over time, I must be decelerating. And because it's still on the downswing of the graph, like all these pieces here, they're on the up, the up, the up, we're moving in the same direction. Now we've changed and we're moving in the other direction now. It's in the opposite direction. This one here, this part here, G, is really hard to see the acceleration, because what we see is we see that there is a decrease in distance. That's what we see, or in the displacement. But it's still like this kind of curve, when we come out like this, is still a gain in. He's just, because we're going in the opposite direction, it's kind of like we've inverted the graph. Instead of doing this, now we're doing this. So here we did this, now we're going to do this. It's a mind shift and it's kind of hard to see, but that's why we talk about it now. And that's why this says displacement. Tough piece, but it's okay. We'll get through it. Questions on this one? Cameron. Why is this one decelerating? Because it's still on this trajectory. Yeah. No, not from G, from A, from our point of where we started. This is the tipping point right here. We're going forward. Now we're going backward. Here, now if they did something here, probably if they're decelerating, but if I had to predict the graph, I would say that it would do this and that they came to rest, right? A horizontal line on a displacement graph is rest. That would be my guess, is the next line if I had to draw it. And then once they leave, they'll do this. And then that would be another change in direction. But we're seeing, what we're thinking is it's doing this and we're going forward, but it's not. They're probably coming to a stop. And then flip it up like this. You got me on that one. That's why I'm pointing out G is being very hard to visualize as acceleration in the opposite direction. This one here, with confidence, I would look at that and know that that's deceleration, because I can see that the distance is decreasing over time. And that's deceleration. This one here, it's got to do with this type of curve, Avery. That it's going out and then coming down. So this is showing a couple of things in one shot. This is showing change in direction. This, if we did this and it went out like this, that would be deceleration, because we could see the line coming to a stop. But it's not. It's just a very bad spot, because we changed direction, and so it's a downward slope. Sorry, I don't have a very good answer for you. But you know what? I'm going to look for a better one.
Is it okay while you're looking?
You can see the bottom of the page while I write this down. Yeah. Okay. This is a velocity time graph. So now we're switching gears in our brain. Oh, it is. How is it in the opposite direction? Because here we identified you're right. It's not in the opposite direction. It's not in the opposite direction because it didn't cross. It's a, oh, no. Okay, wait, now you got me doubting myself, Princess. That's okay. It's okay. That's good. Good. Yes, you may. Uniform motion graphs. Velocity time graph. Object changes direction when it crosses the x-axis. So you're right, it can't be a change in direction. It can only be okay. Very good catch by Princess. And I will show you with the good notes. Very good catch, Princess. And Kyle already said it too. We should give credit to Kyle. I'll pause it. I won't even record it. What's your question? Because the triangle doesn't come all the way down to 0. It's not a perfect triangle. But we need all of that area. We need this part here. How did it get to 10 seconds? All of this distance is also covered. Okay. Daniel. Good question. Any other questions? Those are actually questions that in 7 years, 6 years has never been asked before. All right, do you mind putting it on my phone counter?
Yeah.
You what? Aiden. On it, it's not over 3. Did I write over 3? Here's my paperwork. It's not over 3. I multiplied it by 3. Length times width. Yeah. Okay. Any other questions? Okay, we've got question number 36, 37, 41, 44, 38, 43, and 45. I'm going to split you into teams. You guys are going to be one man short. Avery, Paulina, Kyle, Cameron, Rebecca versus Daniel, Cedric, Joyce, Princess, Aiden, Rayleigh. And we're going to do a race. You can have a collective brain. Oh my God, where are all my brushes? I should take a picture of this before I erase it. And as you get your answers completed, you have to be able to show your work, which means you're not just copying the answers from the thing.
Who wants to work on 45? Excellent. I'll work on question 43.
I have 5.
I'll take question 45.
36.
Oh, I'm good. I'll take the easiest question. Number one. 36. Chapter 1. 36.